So in the previous sections, we were discussing oscillations in time only. However, it is possible to have these oscillations take place or oscillate over space as well as time. So previously, we had displacements that basically just went back and forth. So here on the screen, you'll see a graph in which the y-axis is the displacement from equilibrium, and x is the physical position. So if we have oscillations that just take place in time, what you'll see is them just moving back and forth at roughly the same position. That's the system that we were looking at before. Now, in addition to having them oscillate back and forth at one position, it's also possible for this type of oscillation to spread out or move in space. And that creates something that looks very, very similar to the oscillations we discussed previously. The only difference is there is an additional oscillation in time. So each one of these particular points is taking place at a different time. And so your oscillation appears to move forward in space. And you see this in a number of systems. A beam of light is an electromagnetic oscillation that not only oscillates back and forth, which gives us a frequency, wavelength, or color, but it's also possible for a beam of light to move forward in space. Now, in terms of dealing with this, mathematically speaking, the solution to this comes through something known as the wave equation, which discusses how things spread out in space and time. But again, we're not going to look too much at the mathematical particulars of it. The main takeaway, though, is if we are oscillating in space and time, our oscillatory function, or our sine function, should have part of it that depends on space and part of it that depends on time. Now, the oscillation that depends on time, we've already discussed. It uses an angular frequency and the time variable. We can introduce another component to this sine function that deals with where we are, that's this r position, as well as the wave number, which is basically the space-like equivalent to the angular frequency or angular speed. And so what this gives us is it gives us systems that ripple back and forth in both space and time. And I mean that quite literally. One of the best examples of this is if you fill up a cup with water and you drop a stone in the center, you'll see ripples moving outwards in space as time goes on. And that's what this particular equation describes. Now, interpreting it is very, very, very similar to what we did when we just had oscillations in time, because we're dealing with the same type of function, same type of variables, we just have an additional component for the space. Now, these oscillations can travel in the same direction that they oscillate, travel in different directions that they oscillate. There's no real constraint that it has to look exactly like this. Sound is an excellent example of this. For sound waves, they actually oscillate in the same direction they travel in. So basically, you're left with a wave that oscillates back and forth at the time like this, and then moves forward as it oscillates. And what this creates is it creates areas of high pressure and low pressure, which characterizes longitudinal waves such as sound waves. But typically speaking, mathematically, it's treated very, very similar to the oscillations in time. We simply have an extra component that deals with the oscillations in space.